Okay, so back to what I was saying. You have an e to the negative u. The antiderivative of e to the negative u, you get that. This is your final antiderivative. But then you have to plug in infinity and 0. And I think most students had trouble plugging infinity into this and not knowing what happened. Like they said e to the infinity, that's what they were thinking, I think, immediately. E to the infinity was infinite, so it diverged. But it's negative x squared, so this is really e to the negative infinity, which goes to 0. So just, you got to be careful with that, all right? Now, that's the test I gave last semester. Do not assume you're going to get a problem just like that. Please remember, there's a big frickin' asterisk over everything I'm saying right now. Do not hold me to this. Don't say, well, your review was 10 problems and the first one was like, I mean, this is just an example of what I've given in the past, all right? I'm not going to answer anything. Study your homework. Study the examples done in class, all right? Here's an example of what I've done before. I don't like to recreate the wheel, though, all right? All right, so here we go. Here's the next problem. Find the area under a curve. Okay? Find the area under a curve. The problem with this one, though, is that you have a discontinuity at one of the endpoints. Look, at 1, it's undefined. So this is another improper integral. The wording of finding the area underneath was just to tie the concept of what is it you have to do? You have to integrate the function, right? That's what you have to do. But you have to catch the fact that one of the endpoints causes the discontinuity. Now, ignore, please, some of the notation here, because the way I taught this last semester is different than this semester. We actually came in with a limit, right? We did limit, and whenever you have these endpoints, you'd let t be this one, and then you let t go to 1 from the right side and all that. So that would be a problem. Okay, find the area of the region bounded by these two curves. Sketch the region, label functions, and include details such as intersection points. So I ask for a sketch. I ask for it to be labeled. Here's the intersection. Pretty reasonable functions, wouldn't you say? Quadratic, factored nicely. Set it up, took it all the way through. I didn't say set up only, right? So that had to be taken all the way through. Next one. Same thing, area of the region bounded by these two curves. Now you have to turn it sideways, right? I mean, you have to be looking at integrating with respect to y. Same thing, intersections, set it up, take it all the way. Let R be the region bounded by these two curves with x greater than 0. So you have a parabola, you have y equals x plus 2, and then notice this part right here, x greater than 0. Meant that you do not include this part. That would have caught someone, I'm sure it did catch someone. Include detailed, find the volume of solid generated by revolving R about the x-axis. Include detailed sketch and state the method used. So here's the sketch. Here's the setup. I'm using washers. Notice it's not evaluated. I told them that when I gave them the test. Number 5, you do not evaluate. You just set up the integral. There's the setup. Then part B, take the same region, rotate it around the y-axis now. So this one right here. So shells is much easier to do that way. Or it's much easier to do it if you use shells. Because I'm going around the y-axis this time. And remember, the region that was rotated was only this region. You would have to turn it sideways, and you'd have to do 2 integrals that would be cut right there. One would be here. Parallel to your axis of rotation. Yes. So here, notice I didn't specify what method to use, but shells was so much easier to do that it would have taken a student less time. So that was Now this one, okay, so it's the same functions. Look, same region. This time rotating around the line x equals 5. So if I'm going to rotate it around this line, I'm using shells. What's the radius? 5 minus x. Here's 5. How far away are you from here to here? Well, from here to here is x, right? So 5 minus x. Top minus bottom. Now rotate it around the line x equals -4, which is over here now, same region. Make sense? Here to here is x. Here to here, absolute value of that, distance-wise, is 4. Top, bottom. Shells again, pops its head up. That's 6. Same region around y equals 10. So this time I'm going here, going around. I'm going to want washers now. Measuring these distances from here to here, all the way. That's not right. That's 10. Right. This is x plus 2. X plus 2. So, oh, was I going all the way to the bottom? Okay, I'm sorry. Hold on. I should have kept that. It was hard to see. Where the heck is it? Where the hell is it? Okay, I need you one more time. There we go. Okay, I thought that was going all the way down to the x-axis. That is not going down to the x-axis. That is going down to the bottom of this thing like that. Okay. That's correct. This time the line of rotation is below the region. You get the idea here? Same region around x-axis, y-axis. X is a number on one side, x is a number on the other side, y is a number above, y is a number below. So just getting all the different combinations of rotations that you could have. You got to get that region right, right? Like, well, they had to get that region right, didn't they? All right, the base of a solid is shown below. So I gave them the picture of the base of the solid. Find the volume of the solid if perpendicular cross sections form squares. And we had not talked about cutting the other way. So there was only one way to cut. So these cross sections were always going to be perpendicular to the x-axis. So you come in here, draw your little squares, come up with your formula. Formula only, that's it. Right here, that was the answer. Find the length of a curve. Here's the derivative, slightly different notation instead of y prime. Here's the derivative squared. Here it is, putting it under the root. What was this next step? Common denominator, that made it nice. Went to here. Oh, I did make them go all the way with it. Okay. The answer is 6. Am I saying what? It looks like I had him do the whole thing. Yeah. Yeah, it went from this is my key. This is my answer key. So I'm trying to show as much information without actually, so from here to here. All right, find the surface area, revolving this around the x-axis. Here's your derivative squared, 1 plus here, common denominator. Ah, look, splitting it up into 2 roots again, this canceled. Here, this is a basic integral. U is everything under here. Square root of u is what you're taking the antiderivative of. Blah, blah, blah. There's your answer. Hey. Find the centroid of the homogeneous lamina bounded by these two. Okay, we haven't talked about that. So that was it. All right, well, Monday. Yeah, as far as length of exam, that's a good indicator of length of exam. That's a good gauge of the length. Look, if you get really good at those rotation problems, those go quick. Those can go real quick. That test, yeah.